Hello everyone, welcome to Learniverse. Today I'll be talking about memory layout in C. So coming to the contents, what you will learn today. So we will understand memory layout and its importance, and also we will go through the memory segments where we have different segments. For example, code or text segment, data segment, stack, heap. We'll understand what is the difference between stack and heap and some issues and use cases, and also we will go through dynamic memory, mainly malloc, alloc, free, and what are their best practices, and also debugging and optimization part, and also some key takeaways at the end along with best practices. So what is memory layout in C? So here you can see the different segments that are part of the memory layout. So let's go through one by one. So what is text segment? It stores programs instructions, mainly the compiled code, and it is a read-only segment. Coming to initialized data, here it holds global and static variables that have been given a value before the program runs. And here uninitialized data or BSS section, so it stores global and static variables that are not given a value. They start as 0. And coming to heap section, it is used only when we dynamically allocate memory using malloc or calloc, but we must free it manually. This is one important part. And coming to stack, it stores local variables and function calls. It grows and shrinks automatically, but too many function calls can cause stack overflow. So let's understand when exactly the stack overflow occurs with the example of some code in the future slides. Now let's understand what is code segment, which is also known as text segment. So here it stores the actual machine instructions of your code or your program, and this is the part where your compiled C code resides, and this is typically a read-only section, meaning it cannot be modified during runtime or during execution. So here is a simple code to understand which part of the code resides in code segment or text segment. Here you can see we have a function, and that function is called from main function. So here both function and main function reside in the code segment. And some important facts about code segment. For example, it stores compiled machine code that we need to remember, and also it is a read-only section, mainly to avoid accidental modifications, and it is shared across processes in some systems. These are some of the important facts that we need to remember as part of code segment. And now let's understand the data segment. So in data segment we have two types. One is initialized data segment and another is uninitialized data segment. So first let's understand what is initialized data segment. So here this particular section stores global and static variables that are explicitly initialized before the program runs. So which means here you can see we have a global variable of type int that is initialized to value 10, which means it is stored in initialized data segment. So here I can say global variables with explicit initialization, and also we have a static variable. It retains value between multiple function calls. So here this is also stored in initialized data segment. Now let's understand what is uninitialized data segment. So it is also known as BSS segment. BSS means block started by symbol. So this particular BSS segment stores global and static variables that are not initialized explicitly. So here is a code example. Here you can see we have a global variable of type int. This is stored in BSS segment, and defaultly it is initialized to value 0. And here we have a static variable. This is also stored in BSS segment. And some key facts that are part of data segment is It stores uninitialized global and static variables and initialized to 0 automatically. It saves space because no explicit value is stored. Now coming to stack segment, it is mainly used for function calls, local variables and control flow. Every time when a function is called, a new stack frame is created, and when the function returns, the frame is popped off of the stack, which means whatever the stack frame is created, that will be deleted. Here is a code example, and here you can see the value x is initialized to 10 and it is of type int, and this will be stored in stack. So some key facts are it stores local variables and function calls. So here it is a LIFO mechanism, last in first out mechanism, and it automatically cleaned up when function returns. And coming to size, it is limited. When we exceed the limited size, it leads to stack overflow. So what exactly is stack overflow? It is a common mistake. For example, in this code you can see we are calling infinite recursion function, and again in that function we are again calling this function, and there is no condition associated with this. So it results in stack overflow because it causes an infinite recursion without a terminating condition, which means there is no condition here, there is no base case here. It keeps on calling inside this infinite recursion, again it is calling, so it will never end. So this will lead to stack overflow. Now let's understand heap segment. We can say it as a dynamic memory allocation. Here heap is where dynamically allocated memory is stored using malloc, calloc or realloc function. So unlike stack memory, heap memory must be explicitly deallocated using free. In case of stack memory, whenever the function returns, automatically it was cleaning up, but here we need to explicitly clean up using free function. So here is a code example. Here we have allocated memory in heap using malloc, and some key facts are it is used for dynamic memory allocation. It must be manually deallocated, mainly to prevent memory leaks, larger than the stack but slower in access. Some common mistakes are memory leak. When memory leak occurs is whenever we are forgetting to free memory using free. So suppose we have allocated a memory, and if we are not forgetting to free the memory, then memory leak occurs. So how we can fix this? Whenever we are done with the certain things, then we can, by using a free function, we can avoid the memory leak. So these are some of the best practices for memory management. So use stack for short-lived local variables. Use heap when memory needs to persist beyond a function call, and avoid excessive recursion, mainly to avoid stack overflow. And always free dynamically allocated memory using free function. So these are some of the best practices with respect to memory management. And so let's understand some real-world applications of memory segmentation. When it comes to embedded system, stack optimization for microcontrollers, and also in game development, dynamic memory allocation for large assets. And when it comes to OS, managing stack and heap for processes. And when it comes to databases and HPC, high performance computing, so here efficient memory allocation. So these are some real world applications. So let's summarize whatever we have understood today. So with respect to code segment, it stores programs compiled instructions, which means the machine code. This part is read only. Coming to initialized data segment, it stores global and static variables that are given a value before the program starts. Coming to BSS segment or uninitialized data segment, so here it stores global and static variables that are not given a value. Default value will be 0. Coming to heap segment, it is used for dynamic memory allocation, and memory here must be manually freed. And coming to stack segment, it stores local variables and function calls. Here memory is automatically managed and too many function calls can cause stack overflow. Thank you for watching, and please like, share, subscribe to Learniverse for more such programming content. See you in the next video.